If your goal was to compress an image, would you use a decision tree? Probably not. But can you use a decision tree to compress an image? Yes. I did, and I created what I think is a pretty cool result. I'll explain what I did, and as a bonus, I think it gives a good intuitive sense for what is happening under the hood with the decision tree algorithm. First, here's the image that I'll be compressing. Van Gogh's self-portrait with a straw hat. Now this is just one of the many public domain images available from the awesome people at the Met Museum. So let's start with this image and then take the grayscale version of it. Each pixel here has a location, where it's located along the x-axis and on the y-axis. And each pixel contains a number that corresponds to how dark this pixel is. The ultimate goal that I want to do is create a function that takes as inputs in the x and y locations of the pixels, and what it outputs is the value for that pixel. The most compressed function that I could think of was to simply average all of the pixel values across the entire image. So this is a very, very compressed image. Okay, so let's slowly start to increase the amount of information that's going to be encoded. So here is the smallest decision tree that you could make. It has a maximum depth of 1, meaning that the model looks like this. For every pixel value, it comes in here and it decides, are you above this y value or below this y value? And if you're above, set it to this gray value. If you're below, set it to this other gray value. And you get this image here on the left. So the max depth of 1 means there's one decision and there's 2 different outputs that come from it. Let's bump it 1 level deeper. So now the max depth is 2. The model gets another layer and we double the number of splits and the number of outputs. We get an image that looks like this. It's hard to see here, but there's actually a split here on the left, and so 4 total rectangular regions here. So you get the idea here. So let's fast forward to what this looks like as you really crank the maximum depth to different levels. So along the bottom here, I have the max depth going from 1 all the way up to 30. Now, of course, with color images, there's another detail. RGB encodes 3 numbers for each pixel, 1 for each color, red, green, and blue. The decision tree, when trained on this, will separately solve each color layer, and we can combine them to see what that looks like in the end. And we get something that looks like this, which, as you can see, the max depth cranking up really starts to encode the information to the point where you're encoding all of the information, essentially. Now, in my reading of color encoding, I found that mathematical operations like averages, which is what's happening here, aren't really a valid operation on RGB encodings, and what I found suggested that HSV encodings, or hue, saturation, and value, is a little bit better. So I did both. Here's what they look like side by side. And I think I'd give the edge to HSV. It looks like it's getting sharper a little bit faster at the same maximum depth, but it really wasn't as dramatic as I was expecting. Anyway, all the code that creates both the animations as well as the decision trees that encode this information can be found in the link in the description below. I coded this whole thing up using Jupyter Notebook in VS Code for the first time. And I also used NBDev for the Python module development. I'll be going into what I learned and how I refined my workflow in a future video, so subscribe if you're interested in that kind of thing. And ask any questions you have in the comments. See you next time.